Okay, we're going to take a look at some very special types of subspaces of Rn or Rm, right? Depending on whether we're talking about rows or columns of a given matrix here. And then we're going to talk about what's called the null space or the kernel of a matrix. And these are very important subspaces that we'll use for, I would say, the rest of the course. And if you go on to do anything more mathematical versus, like an engineering route or something, if you were to go more along the lines of like an applied math route or something, you will see and use this stuff almost every day. So let's start with understanding what the row space and column space of a matrix is. Let's let A here be an m by n matrix. So we have A11, et cetera, A1n, A1, AMN, right? So here's our m by n matrix. We have a notion of row vectors and column vectors. And so what are the column vectors? Well, the column vectors here are, you just take in the first column, you consider that as its own vector. So we have A11 all the way down through AM1, right? The next column vector would be A12 down through AM2, and then et cetera, all the way over to A1n down to AM n, right? These would be your column vectors. And we'll call the column space. So here's like a definition. The column space of A is the subspace spanned by these vectors, A11 through AM1, et cetera, A1n through AMN. And so really the column space is just the span of the column vectors of a matrix, right? We call this maybe I'll write it, the definition in red here. This is the column space. Okay, cool. What about the row space? Well, you may be able to kind of guess what the definition would be. Well, what are the rows? What are the row vectors here? The row vectors are going to be, well, really, it's going to be like A11 through A1n, A21 through A2n, et cetera, and then M1 through AMN. These would be your row vectors. And then so the row space of your matrix, so row A, this is going to be defined to be the span of those vectors. So the span of A11 through A1n, et cetera, AM1 through AMN, right? All these vectors, these span the row space. It may be more convenient to write this as, like A11 through A1n transpose, AM1 through AMN transpose. You could see it written like this also, but we keep the row or column, whether it's a row or column vector, we keep that specified here, right? And so that's important to note. Okay, I guess I should say here, this was the row space. Okay, now let's see some important facts we have about row space and column space, and then let's do a couple examples here. So we have the following proposition. let's let B be an M by N matrix obtained from A by elementary row or column operations. You know, we could do all of these row operations where you take like, you know, you swap two rows, you take a linear combination of two rows and replace a row. You could do all of that with columns as well, right? And really, if you want to think about it, you say, what would that be doing if I were to do column operations instead of row operations? Really, what that would be doing is row operations on the transpose, right? Because what is the transpose of a matrix? Remember, a transpose of the matrix is where you flip along the diagonal, or you think about swapping columns for rows. And so really, doing row operations on the transpose is the same thing as doing column operations on the original matrix. So there's no reason we couldn't do column operations. And so let's say that B is obtained from A either by only row operations or by only column operations, right? Not a combination of the two. So then, well, operations, then the row space of B is equal to the row space of A. Or if you did column operations, the column space of B would be the same as the column space of A, right? And so this is respectively, meaning here, if you do row operations, your row space is preserved. And if you do column operations, your column space is preserved. There's no guarantee of if you do column operations that your row space is preserved, right? So I want to mention that this is purely respectively. So if you do row operations, the row space is conserved. If you do column operations, the column space is preserved. And we have another proposition here. That's an important property. So let's let R be the reduced row echelon form of the matrix A. Then the non-zero rows of R form a basis of, well, they form a basis of the row space of the reduced row echelon form matrix. But this is obtained via row operations, so we know that this would be the same as the row space of the original matrix A. So what you can do, and we'll do this in an example here, is you can take a matrix A and say you want to calculate its row space. Well, to calculate its row space, the easiest span, or kind of the most simplified vectors you could find to span your row space would be, first you take the matrix A, you simplify it to reduce row echelon form. You look at the non-zero rows, or you look at the rows corresponding to pivot entries, right? Any row containing a pivot entry is going to be a non-zero row. Those row vectors form your basis, right? And so we'll look at that a little bit here. Okay, let's do an example. Let's say we have the following 3x5 matrix here. We have 1, 2, 1, 3, 2, 1, 3, 6, 0, 2, and then we have 3, 7, 8, 6, 6. And we want to find the rank, the row space, and the column space of A. Now, just to enhance intuition here, why all of a sudden do we care about the rank again, right? Well, let's think about this before we actually solve this problem. here, the number of rows of R, or excuse me, the number of non-zero rows of R form a basis, right? And the number of non-zero rows of R, well, this is going to be the same as the number of pivots. Right? Because if you have non-zero rows, well, then once it's in reduced row echelon form, the leading entry has to be a pivot position, right? And so if your leading entry isn't a pivot position, then you have a row of zeros. But what's the number of pivots? We called this the rank of A. But what's the number of non-zero rows of R? Well, those form a basis. And what's the number of basis elements? Well, that's the dimension of the row space, right? So row A. And just by this understanding, we actually just came to the conclusion of a very important theorem, that the rank of a matrix is actually just the same as the dimension of the row space. And so we'll see that here as a theorem in a little bit, but we can deduce that purely from this understanding of, well, the number of non-zero rows of my reduced row echelon form is the same as my number of pivots. Well, then by the transitivity of equality here, then the dimension of my row space is defined to be the rank here, which is pretty cool. Or how about the rank is defined to be the dimension of the row space? So with that in mind, let's calculate the rank, the row space, and the column space. Well, how do we find the rank, right? We have to find the number of pivot positions. To find the number of pivot positions, let's put this in reduced row echelon form. So what's the first thing I would do here? Well, the first thing I would do in putting this in reduced row echelon form is I would say row 2 is going to be replaced with row 2 minus row 1, and row 3 is going to be replaced with row 3 minus 3, row 1. This is going to give us, well, let's see, we didn't do anything to row 1. What do we have for row 2 here? It looks like we're going to have 0, and then we'll have 3 minus 2 is 1, 6 minus 1 is 5, 0 minus 3 is -3, and 2 minus 2 is 0. For row 3, we have 3 minus 3 is 0. We have 7 minus 6 is 1. We have 8 minus, where am I? Sorry. We have 8 minus 3 is 5. We have 6 minus 9 is -3, and then 6 minus 6 is 0. Well, here we notice that row 2 equals row 3. So let's say row 3 is equal to row 3 minus row 2. This gives us the matrix 1, 2, 1, 3, 2, 0, 1, 5, -3, 0, and then 0, 0, 0, 0, 0. Right? We are not quite in reduced row echelon form yet because we still have this 2 above the 1 in the second column, right? So how do we get rid of that? Well, we can get rid of that by saying that row 1 is equal to row 1 minus 2 row 2. And then if we do that, we will get the following matrix. We'll get 1, 0, -9, 9, 2. I'm just copying it here so I don't have to flip back and forth between the two pages so much. And then 1 or 0, 1, 5, -3, 0, and then 0, 0, 0, 0, 0. Okay. Now, what do we look at here? What are our pivot positions? We have 2 pivot positions, which implies that the rank of A is 2. Cool. We found the rank. Now we need to find the row space and the column space. And what did we have in this previous proposition? The number or the non-zero rows of R form a basis of the row space. So we take the non-zero rows. So we have two non-zero rows of the reduced row echelon form, and those vectors form a basis. So that means that the row space of A is going to be the subspace spanned by the vectors 1, 0, -9, 9, 2, and 0, 1, 5, -3, 0. And notice the, and maybe now here you can understand more why there's a one-to-one correspondence between the number of non-zero rows and the number of pivot positions, right? Well, for every row that has a pivot position, it's necessarily a non-zero row, vice versa. If you have a non-zero row, you have a pivot position. And if it's not a 1, then you just divide through by 1 over whatever it is to get the leading entry to be 1. And since we have this one-to-one correspondence, we see what's the dimension of this row space, right? Well, the dimension of this row space of A is necessarily 2 because it's the number of basis elements. How do we find the column space though, right? We still take the number, we still look at the pivot columns this time. So we look at the pivot columns and it's the first two, but we are not guaranteed that under row operations that the column space is preserved, right? Under row operations, we were guaranteed that the row space is preserved, but not the column space. And so for that reason, to find the column space or the vectors that span the column space, you have to go back to the original matrix. And so that would be these. That would be these here, right? And so what we have is the column space of A is the space spanned by the vectors 1, 1, 3, and 2, 3, 7. And if you were to have done column operations on this, and you put this in a reduced row echelon form via column operations, right? Well, then you would have that your column space is preserved, and then you would have to go back to the original matrix for your row space. But since we only ever do row operations, when it comes down to finding the column space, you look at the pivot columns, and then you go back to the original matrix, and then those columns are your basis vectors, right? Okay, let's do another example. Well, before I do another example, maybe let's stop and give a formal definition now. We can define the rank of A to be the dimension of the row space of A. So we can define it this way, not only, or so without talking about the number of pivot positions, right? You can just look at the dimension of the row space and understand the rank that way instead. If in the given context, that's easier to understand. Let's do another example here. Let's find the same things. Let's find the rank, the row space, and the column space. Here, A is going to be the following matrix: 1, 1, 1, 1, 2, 3, 2, 3, 1, 6, 1, 2, 3, 0, 3, 4. And 2, 2, 2, 0. Okay. Well, for the sake of time, I probably won't convert this to reduced row echelon form. I wanted to, in this example, take the time to just kind of refresh, make sure we can still do this, et cetera, et cetera. But here, let's just say, after a bunch of row operations, we get the reduced row echelon form of A, and it's going to be the following matrix. What I got was 1 0 0 0 0 1 0 0 0 0 0 1. Whoa. Just kidding. How about 0 0 1 0, and then 0 2 negative 1 0, and then 13 halves, negative 5 halves, 1 half, and 0. So let's find the row space. The row space of A is going to be spanned by the basis vectors consisting of the non-zero rows. So what are the non-zero rows here, right? Well, we have 3 non-zero rows. The bottom one is entirely a 0 row. So it looks like the row space is going to be, and I'm going to write these as transpose here. So we have 1 0 0 0 13 halves, transpose 0 1 0 2 negative 5 halves, transpose, and sorry, I ran out of room for the third one. It's 0 0 1 negative 1 1 half, transpose, right? That is exactly the 3 non-zero rows of the reduced row echelon form of the matrix A. This makes up your row space. Now, what does this mean the rank is? Well, by definition, that's the dimension of the row space of A, which is 3, because that's the number of basis elements we have, right? Cool. Now, what about the column space? For the column space, you find all pivot columns. In this case, it is the first 3 columns. These are your pivot columns, which means the vectors that are a basis for your column space are the corresponding columns in the original matrix, right? So that would be columns 1, 2, and 3 in the original matrix, which means that we have the column space is spanned by the basis vectors 1, 1, 1, 1, 2, 3, 2, 3, and 3, 0, 3, 4. Okay, so we found the row space, the column space, and the rank of the matrix here. Now, one thing you may have also noticed, right? We kind of made this observation earlier here. Where are we? We made this observation that the rank is actually the same as the dimension of the row space, because it was all related by the number of pivots, right? The number of pivots here was really dictating the dimension of the row space, and it's also dictating the rank, which we now know to be synonymous. But if you'll look, the number of pivot positions or pivots was also dictating the number of pivot columns, right? And so here we had 2 pivot columns, which led to 2 basis vectors, which led to the dimension of the column space in this example to also be 2. In this example, we had 3 pivot positions or 3 non-zero rows. And because we had 3 pivot positions, that means we had 3 pivot columns, which means that the dimension of the column space in this example was also 3. This turns out to be true always. And because of that, we have the following theorem: that the rank is the same as the dimension of the row space, which is also the same as the dimension of the column space. And so really, to find the rank, you just need to find the number of non-zero rows or pivot positions or the number of pivot columns, right? There are so many different ways we can think about the rank here, and they're all the same, right? Because it all comes down to that they're the same like the same number of pivot positions here in this reduced row echelon form. So when you have a matrix and you're looking at the column space and the row space, the dimension of these spaces will always be the same, and it is the rank. Okay, from this theorem, we have a lot of results kind of immediately just from understanding this theorem here. So we'll list this as a corollary. The first is that the rank of a matrix A is the same as the rank of its transpose. Well, that makes sense because when you take the transpose, you swap the rows for the columns, but the dimension would be unchanged, right? If you swap the dimensions, well, the dimensions are the same, so the rank's going to be the same. We have that if A is an M by N matrix, then the rank of A cannot be greater than M, and it cannot be greater than N. If you would like to see this written differently, you could say, or that the rank of A is less than or equal to the minimum of M and N, right? Because you could never have that the dimension of the column space is greater than the number of columns you have, right? Or you could never have that the dimension of the row space is greater than the number of rows that you have. And that's exactly what this is saying. So we have, what else do we have? If A is a square invertible matrix, or sorry, let's just say A is an N by N square matrix for now, then A is invertible, meaning A inverse exists if and only if we have max rank, meaning that the rank of A is the dimension of the number of columns and the number of rows, right? And so you can only have an invertible matrix of max rank. If you have rank less than N, this matrix will not be invertible. Lastly, we have if B and C are two invertible N by N matrices, then the rank of A is the same as the rank of BA, which is the same as the rank of AC. Okay, and this kind of wraps up the important results we get just for understanding that the rank, the dimension of the row space, and the dimension of the column space are all the same thing, right? There are so many different ways to interpret the same thing, and it's important to understand how to interpret all of them depending on in what context it would be more beneficial to interpret the rank through a certain lens, right? So I think we'll stop this video here. And we've seen now the row space, the column space, some properties, its relationship to the rank, and two examples. What I want to do next is the same thing, but for the null space or the kernel of a matrix. And we'll basically give the kernel a similar treatment to what we've done here for the column space and row space.